we need a good way to identify what substance it is that we encounter in the laboratory. We don't want to have a specific method for every kind of substance because there's just far too much variety, and that would be more cumbersome than we could deal with. So what we want is something that we can just throw anything at it and it's going to work. Well, an insight into that might be that we have established that everything is made out of elements, and that the way those elements combine is what gives us the unique substance that we deal with. So maybe we can go ahead and decompose our substance into elements, and we can quantify that composition, and that will be how we come up with an identity for the substance, or at least help to characterize it. So one of the ways that we are going to present this information, if we do our experiment, we're going to collect some information about the mass of each element in our substance, and we will present that as a percentage. So we will tally up, for example, all the carbon atoms. So maybe we have something like CH2, CO3. So we would add together this 12.01 grams per mole and this 12.01 grams per mole, and then we'll divide it by the mass of the molecule. So all these atoms added together, and then multiply by 100 to make it a percentage, and that will be the fraction of carbon which comprises this substance. Well, let's say we took some sucrose, that's common table sugar, C12H22O11, and we threw it in our mass analyzer. What's our mass analyzer going to spit out as the characteristic composition of sucrose? Well, the first thing we're going to need to do is to calculate the total weight of this molecule. So take our 12 carbons, and we look in the periodic table, and it says that carbon weighs 12.01 grams per mole. So 12 times 12.01 plus our 22 hydrogens, each weighing 1.01 grams per mole, plus our 11 oxygens, each weighing 16 grams per mole, and our total is 342 grams per mole. Now that we know that, for each individual element, we are going to calculate the percentage. So we have 12 carbons, each weighing 12.01 grams per mole. So that's our total mass for carbon. We put that over our total mass for the molecule, times 100 to make it a percentage, get 42.1%. Done the same thing for hydrogen, and the same thing for oxygen. And a good check once you get done with these problems is to make sure this adds up to 100%, which in this case it does. If it didn't, that would probably mean we'd made an arithmetic error somewhere. Once we have our mass composition data, we can use that to come up with an empirical formula, which will describe the ratio of the different elements to one another in our substance. For example, here we have C2H4, and 2 carbons to 4 hydrogens. That's a 1:2 ratio in the simplest form. So we write CH2 for its empirical formula. And over here we have a substance with 4 carbons and 8 hydrogens to go along with them. That's still a 1:2 ratio. So this has the same empirical formula. Why would we have a formula like this? Well, our machine is not going to tell us the number of atoms in a molecule. It's just going to count up all the total number of carbons and the total number of hydrogens. So this is actually going to be the only thing that the machine can give us, is this empirical formula. We're going to have to use other insights to come up with the molecular formula. But this is a good stepping stone to doing that. So in order to come up with these formulas, the first thing we're going to need to do is calculate the number of atoms of each type we have. So presumably, we will identify the total mass of atoms of that type, and we'll convert it into moles, and then we'll take the ratio of moles of one element to the ratio of the moles of another element to give us this empirical formula. And we're going to want to convert to simple whole numbers because we can't have fractional atoms, so we want to represent that in our formula. And we'll go ahead and write it in simplest terms. So if I had C2H4 here, then I'll write it as 1/2 rather than 2/4. All right, so we use our mass spectrograph and we analyze a compound in our laboratory. And we find out that it is 48.64% carbon, 8.16% hydrogen, and 43.2% oxygen by mass. Knowing that, can we reconstruct its empirical formula? Well, we can. First thing we're going to need to do is calculate the number of atoms of each type. Now, there's a problem here that we don't have any masses in this problem. But what we can do is we can use that law of definite proportions of constant composition, which says that no matter what sample we have of the substance, we're always going to get the same formula for it. It's always going to be the same substance. So we can choose an arbitrary sample size. So let's say that we have 100 grams of our sample. Well, in that case, 48.64% would be 48.64 grams for carbon. And so that will make the math really easy. And now, once we calculate the empirical formula based on this 100-gram sample, that will be the same empirical formula that applies to any other sample. Once we have our mass composition data, we're going to want to convert that to moles. Moles is usually what we do calculations with, and mass is what we just happen to be able to measure on our instruments. So we'll look up in the periodic table and see that it's 12.01 grams for every mole of carbon atoms, times 48.64 grams of carbon gives us 4.05 moles of carbon. Now we're going to do the same thing for hydrogen and oxygen. Convert our masses into moles, about 9 moles of hydrogen, about 2.7 moles of oxygen. Now that we know the quantity of atoms, we can figure out the ratio of carbon atoms to hydrogen atoms to oxygen atoms. Now, there's a hint here. Usually it will work out best if you construct these ratios using the atom which has the least quantity, in this case oxygen. That will just make the ratios you come up with easier to figure out what their simple whole number equivalent should be in many cases. Let's go ahead and do that for carbon and oxygen. So we take 4.05 moles of carbon to 2.7 moles of oxygen. It comes out to 1.5, which we can represent as a 3:2 ratio. 3 divided by 2 should give us 1.5. Now we'll do the same thing for hydrogen to oxygen. 9.069 divided by 2.7 equals 3.36. To me, this looks very close to 3.33, which would be 3 plus an extra third, which would be 10 thirds. So that's a 10:3 ratio. And of course, oxygen is going to have a 1:1 ratio with itself. Now that we know these ratios, we can incorporate them into our empirical formula, which is just a compact way of expressing them. So let's start. We can pick any of these ratios. Oxygen is already going to be true no matter what. It's 1:1. So for our next one, let's go ahead and do this carbon to oxygen. So that's a 3:2 ratio. The way we write it in our empirical formula is we just put those coefficients in. So we're saying that there's 3 carbon atoms for every 2 oxygen atoms. Now we're going to need to build in our last remaining ratio, the 10:3 relationship between hydrogen and oxygen. Now this is a little bit tricky. We want to make sure that we preserve this 3:2 ratio between carbon and oxygen. But in order to write this 10:3 in here, we're going to have to adjust our number of oxygen atoms. Now the easiest way to set this up so that we have a common factor that we can use is if we just go ahead and multiply this 2 times this 3. So we'll call that 6 oxygen atoms. Now if we triple our number of oxygen atoms, we're also going to have to triple our number of carbon atoms in order to maintain that 3:2 ratio. Now we have double this 3. We have 6. So that's going to be a 20:6 ratio of hydrogen to oxygen. And so this is our final empirical formula. C9H20O6 And there's nothing that we can divide out of this to make it any simpler. Probably we're not content being able to just find empirical formulas. We'd like to know the actual number of atoms in a molecule, which is what's given by a molecular formula. Well, this is going to be some multiple of the empirical formula. So here we have a couple of cases. C2H4, we have 2 carbons and 4 hydrogens, but the simplest way to write that ratio is 1 to 2. So the empirical formula is CH2. We also have C4H8 with 4 carbons and 8 hydrogens. This is again a 1 to 2 ratio, so the empirical formula will be CH2. Well, if all our instrument can do for us is figure out the amounts of carbon and the amount of hydrogen, then it's not going to be able to distinguish between these two compounds, which have the same relative composition. But if we were able to measure the molecular weight for these compounds, that would distinguish them. It's 28.05 grams per mole for our C2H4, and it's 56.11 grams per mole for our C4H8. And these are all multiples of our base mass, the formula mass, CH2. If we add up 1 carbon and 2 hydrogens, we get 14.03 grams per mole. So this is 2 times that mass. This is 4 times that mass. And a funny coincidence, if we take 4 times our empirical formula, we get that molecular formula. So that's going to be our method to figure out the molecular formula. If we can measure the molecular mass and compare it to the mass from our empirical formula, which is kind of fictional, then we can figure out how many of each atoms exactly we do have. Our steps to find a molecular formula are going to be largely based off of what we did previously. The first thing we have to do is we have to find the empirical formula. Now, once we have found the empirical formula, we are going to take the molecular weight that we know and divide it by the weight that we calculate for the atoms in our empirical formula. And we're going to use that number, and we're going to multiply all the subscripts in our empirical formula by that number. Now note that when you do step 2, you should get a nice whole number. And if you don't get something very close to a whole number, then you know you made a mistake in your empirical formula, because you're not allowed to chop molecules in half or into thirds in order to make the math come out right. So you must have made a mistake somewhere further back. For the sake of brevity in this next step, let's assume someone's already done the hard work for us. They figured out the empirical formula of a substance and found it was C2H8N. And we're also able to measure that it had a molecular weight of 180 grams per mole. Now, knowing this information, what is the actual formula for the molecule? Well, we've already done our first step, which was to find the empirical formula. Our next step is that we need to calculate that weight ratio between this formula and the mass that we were given for the molecule. So let's add together these 2 carbons, 8 hydrogens, and 1 nitrogen. You get a total of 46.11 grams per mole. 180 divided by 46.11 grams per mole comes out to 3.9, which is close enough to 4. And again, if it's not very close, you probably have a wrong empirical formula. Now that we have this number, we're going to use it to adjust our empirical formula. So multiply all the subscripts by 4. So we actually have 8 carbon atoms, 32 hydrogen atoms, and 4 nitrogen atoms. If we add up all the masses here, it should come out pretty close to 180. I think it comes out to 175 point something. It's actually kind of amazing that we can take just about any substance and characterize its molecular makeup just by throwing it in our mass spec machine and doing a little bit of arithmetic after the fact. Well, we might not have a mass spec machine, That's okay. There's a variety of techniques that we can use to determine composition of substances. And depending on the substance, some of them are very effective. One of the more important ones is combustion analysis, used a lot in analytical chemistry. So this is where we take our sample and we combust it, we burn it in the presence of oxygen, O2, and completely convert it into products. What that does for us is it makes it so that we can measure the products and infer what the original composition was. For example, if there was any carbon in our sample, it will be completely converted into CO2. Any nitrogen will be converted into NO2. Any sulfur will be converted into SO2. Hydrogen, every 2 hydrogen atoms will combine with oxygen to make H2O. And in many cases, it's very straightforward to measure these product gases, which makes it very straightforward to then know how much of these elements were in our sample. Now, this doesn't work for other elements, so we're going to need a sample that's only comprised of these 4 things at most, or some minor subset of them. One very important subset is what's called the hydrocarbons, substances containing only hydrogen and carbon, things like gasoline, other petroleum products. And these are going to have the reaction that we take our substance made up of carbon and hydrogen. It will react with oxygen, and the carbon will become CO2 molecules. The hydrogen will become H2O molecules. And if we count the number of CO2s, that will also be the number of carbons that was in our original substance. And if we count the number of H2Os, we can see that there will be twice as many hydrogens that were present in our original substance. Now, we have to be careful here that we don't want to count the atmospheric oxygen, because we are absorbing some amount of oxygen, we don't know how much, in order to react this substance and get it into the CO2 and H2O. So if we counted up the oxygen atoms on the right side, they would be some unknown mixture of oxygen, which was in our sample, and oxygen, which was influxed from the atmosphere. So what we have to do instead is that we take our sample mass and we subtract away the mass of the carbon and the hydrogen and anything else that we can figure out. And whatever mass is left is going to be the mass of our oxygen. Let's use our combustion analysis to determine the molecular formula for ascorbic acid. This is vitamin C. You're warned this is going to be a little bit more involved since we're going to be tying all of our steps together. Now, we've already done some experiments and we figured out that carbon, hydrogen, and oxygen are the elements which make up this ascorbic acid. And so we take a little piece of our ascorbic acid weighing 0.19 grams and we put it in our oven, get it really hot, convert it into gases. And we find that 0.286 grams of carbon dioxide gas is produced and 0.0782 grams of water gas is produced. We're going to do some other experiments and find that the molecular weight is approximately 180 grams per mole. Now, knowing this, what is the molecular formula of ascorbic acid? Well, the first half of our problem, the major portion actually, is to figure out the empirical formula. So to do that, we need to calculate the number of atoms, the number of carbons, and the number of hydrogens, and anything else, and construct their ratios. And that's what the empirical formula represents, is the ratio of atoms. So let's start with the carbon. So every carbon atom in our sample is being converted into a CO2 molecule. And we have measured the number of CO2 molecules in terms of mass. So we can use our periodic table to get the molecular weight of 1 carbon and 2 oxygens. It comes out to 44.01 grams per mole. So we convert our 0.286 grams of CO2 into moles of CO2. And now we use this equation, which says that there's one carbon atom for every one CO2 molecule. So we write that ratio. And you can think of this as canceling out our CO2s as well as the grams. So now we're going to be left with moles of carbon. Do the same thing for hydrogen. Note that for hydrogen, we have a 2-to-1 ratio. So we'll take our mass of H2O that we know and convert it into moles of H2O, then use this 2-to-1 ratio to get into moles of hydrogen. We get 0.00868 moles of hydrogen. Now remember, for our oxygen, we can't calculate it directly because we've incorporated into these gases some oxygen from the surroundings. So instead what we're going to do is we're going to take the mass of our sample and subtract the mass of the carbon and the mass of the hydrogen, which we can calculate because we know the number of carbon atoms and the number of hydrogen atoms now. So we'll take our sample mass of 0.191 grams, subtract our number of carbons, 0.0065 moles, times the molecular weight of carbon, which is 12.01 grams per mole, and subtract also the number of hydrogens times their molecular weight, and we get 0.104 grams of mass, which must be the missing mass from oxygen in our sample. As with our other elements, we'll want to convert into moles. So take our mass of oxygen that we've calculated, multiply or divide by its molecular weight in the periodic table, and we get 0.0065 moles of oxygen. Now we have the quantity of all of our elements. The number of carbon atoms, the number of hydrogen atoms, the number of oxygen atoms. To get our empirical formula, we're going to construct those into ratios. So we'll go ahead and put the substance which has the smallest quantity of moles in the denominator, just for convenience, and that's oxygen. So we put oxygen in the bottom, and it has the same number of moles as carbon. So I guess that's also the smallest quantity. You could have used either of these. So we clearly have the same number of carbons and oxygens. Construct a ratio of hydrogen to oxygen. Comes out to 1.34, which I say is pretty close to 1.33, which I recognize as 1 1/3. So that would be a 4-to-3 ratio. And oxygen, of course, has a 1-to-1 ratio with itself. Now we can write these ratios as an empirical formula. So hydrogen is 4-to-3 with oxygen. And because carbon is 1-to-1 with oxygen, that means we must now make sure there are 3 carbon atoms. And that will give us the needed 1-to-1 ratio. The last piece is to take our empirical formula that we've come up with and combine it with the information we have about the weight of the molecule. And this will allow us to convert our empirical formula into a molecular formula. We need to take the weight that we would have for our empirical formula, if it was the molecular formula, tally up the masses of all the atoms in that. We had our 3 carbons and 4 hydrogens and 3 oxygens. And then we put that in a ratio with the weight of the molecule. It comes out to a multiple of 2. Remember, it should be a nice whole number here. You don't want to go about chopping any molecules into pieces. So now that we have that factor, we can go ahead and multiply all the subscripts in our empirical formula, and that will give us the molecular formula. So we've decided that ascorbic acid is C6H8O6. Now, what's really incredible about this is that we never had to inspect any individual molecules. We never actually isolated molecules from each other independently. We were able to just take all of our aggregate information and put it together in order to determine the exact composition.